University of Wrocław, and he will tell us about black hole versus dark matter model.
Thank you.
The floor is yours.
Thank you for introduction, and I would like to thank the organizer of the possibility to be here and to give this talk. Part of the results that I will present here are obtained with Dafermos from Łódź. And I will start with some credit to Smoluchowski, who is well known here. He didn't consider this equation, but I was trying to make research on this equation. If you forget about p prime in this equation, putting it 1, like for ideal gas, then this p prime becomes 1. Then you have just normal diffusion term and transport term. And this equation was considered by Smoluchowski, but without this inverse of Laplace operator on the very end, which in fact comes from the Poisson equation. So here was potential generated by the density rho, and so then it was just linear. So what we were doing, we were considering this equation above, existence, global existence, blow-ups, depending on the data. The data that were available in this model was mass of the system and temperature, or mass and energy. If we had mass and energy fixed, then the temperature might be time dependent, but it was just given by algebraic energy equation. And all of these models were with the pressure P, temperature theta, D is dimension, which should be free basically here, and rho is the density. And P is a given function giving the pressure. So this was the whole pressure. And you see that if P is identity, then you have the simplest Maxwell-Boltzmann. And this equation comes from Fokker-Planck equation in the phase space for the distribution when there is velocity. And how to get this, let's say, hydrodynamic equation from Fokker-Planck, you average over velocities, which is standard formula. And there is also some high friction limit, Chapman-Escock approximation at maximum entropy. So there are some procedures, let's say, but this equation, as I wrote above, is non-relativistic. So when in 2020, more or less, the Nobel Prize was given to Andrea Ghez and Reinhard Genzel, here is the picture, just skipping, here is the picture of Smoluchowski, and there is a famous mountain in Tatra Mountains, which is Monk, and here is myself, and the mountain is Andromeda. The name is Andromeda, it's in Rocky Mountain. Yes?
Excuse me, is it a multiplication of a Laplacian times its inverse?
Here is Nabla, which is Radian, and here is...
This is grad. This is grad of the potential. So this is
so yes, here is potential. There is potential.
Yeah, so there's potential.
In any case, if we multiply an operator by its inverse, we usually get identity, yeah?
But grad is not inverse to Laplacian. It is first order.
This is the first order operator, yes, and this is the second order.
But this is not inverse.
This is not inverse.
This is not inverse.
Okay. So coming back, here are some collaborators from Wrocław, Nadzieja, who recently died, unfortunately. Wheeler, with whom we stated this, let's say, general formula as sufficient condition for the entropy to exist when the energy was fixed. So somehow, and this suits to many statistics as I listed here. Bohr's, I mentioned the results here are, and there is French school, Dolbeau and Chavanis. And coming back to my time in Łódź, Kosinski, who was my teacher at the physics department, but only about Korteweg-de Vries equation and inverse scattering method, not relativity. So coming back to relativistic equation, we should go to, we should go to Remo Ruffini, who was a student some time ago of Wheeler, and there is the quotation from the book of him with Ohanian about general relativity, and my aim was somehow to replace this equation with relativistic one and to replace the equation of state with the relativistic one. So that's the approach, and see what can be said about for this equation. There are the notion of gravothermal catastrophe. Gravothermal, since either the density can be high or you have to take care about the temperature as well. That's why gravothermal catastrophe. And we fix energy, but if we fix temperature, then it's something that is called isothermal collapse. So we move to. So here are two astronomical phenomena. One is from about S2, which basically means that that I mentioned this Nobel Prize winners, this close to elliptical trajectory of something inside our Milky Way. And here is something which is called Hill's mechanism, and it's recent by Koposov. This was binary stars, and one of them was ejected from our Milky Way, and the other one stayed, let's say. Okay? And here are some references. So let's say my main motivation is the last paper. You see here the Ruffini, who is at the end, and he suggested, because with this Nobel Prize winner, they suggested there might be something massive inside our Milky Way. But they didn't claim whether it's black hole or something else, and they tried with other guys here, they tried to fit the data for this S2 trajectory with dark matter model, which means basically that you have continuous distribution of the mass. But sometimes it also might be singular at zero, but we'll skip it. We'll think about continuous rather. And the paper about this ejection of this one of the stars in binary system was here by Koposov. And this Bondi I gave just for showing that what we will also try to do is to find for some systems, for stars or galaxies, some bounds on the mass. So this is our aim. If we just try not to think about Milky Way, but about any, let's say, system with some equational state. So we start, as always, with Einstein equation that you know. And what is, with this dark matter model, the main thing is that in T, you have to have the density and the pressure. And they should be related by the equation of state somehow. So that's the approach. And here is just the curvature, and I just wrote to show you this is with this continuous with dark matter model, and here is with Schwarzschild solution for black hole. So I will just list, but it's let's say, standard. Here, this coefficient, as you see in dark matter model, is more complicated. And what we assume with this, let's say, models is static and symmetric. So these are two assumptions. M is the mass of the system. And here is another equation following from Einstein equations. And finally, we end up with Tolman-Oppenheimer-Volkoff equation, which is well known, not only because of the movie that was about Oppenheimer recently, but, and here you see that in this equation enters density and the pressure, mass as well. And it all depends in which way rho depends on P or the other way around. So you can, if you have equation of state, you can reduce one of them. And first approach is very naive. It has some appeal because it's mathematically, let's say, the easiest to handle. And we will see there is some nice phenomena. If you change the variables in the Milne style, let's say, and you assume that you have P equal to rho, so let's say linear model, that the simplest possible. We will move to nonlinear ones, but in a moment. Then you end up with very simple dynamical system in two variables, x and y, and you should remember that x is more or less mass. This is the thing, and y is more or less the density. So on this axis that we will see in the moment, we have mass versus density. And here is here's phase space. And here, what we can see here is, because in fact we are looking for just one trajectory. I will show you this trajectory first. Here or here.
But you said that you have a static system.
Static system, yes.
So what do you mean by it?
Yeah, I cannot move. Right? Oh, yeah. So you see that here the time on this dynamical system corresponds to logarithm of a radius. So there is no time.
X and Y is
X and Y is mass density, and time in this, let's say call it time, in this dynamical system, in fact it's logarithm of the radius. So coming back to this, we look for this one trajectory that I've shown you here, which connects two critical points. One is 0, 0, not very interesting.
On the parallel axis and
yes, so here we have the mass, here we have the density. And what we do, in fact, we fix the mass, and take this part up to the given mass, this part of this trajectory, as the density, let's say. This part should be translated to the density profile. So what you can see, which is interesting, that this is numerics. So you can see there is some critical mass above which you don't have any solutions.
Could you remind the definition of this mass?
Yeah. Here it's up to the scaling, because here it's something easier. It's without this 8 pi. I will show you another one, but let's say it's x could be thought vaguely as the mass. Yes? With rescaled argument, okay?
And what is x?
Sorry?
X, what is
X is on this. X is the axis. Yes, it was the definition and X is the axis. So, as I told you, here you should think about the mass, and here you should think about the density for the system. So, coming back to this, here we have spiral which converges to this fixed point, and this fixed point corresponds to singular density. So this fixed point, if you translate it to the density, it's a singular point. So it's the density which is 1 over r squared, which is sort of Chandrasekhar solution. But what we do, as I told you, we fix the mass, we take this part, and this should be our solution. So you see that for some intermediate values there are more solutions, but probably only one would be stable from them, the one that doesn't make circles, let's say, this monotonous one. But also you can see there is some values of the mass when you have no solutions. And this function, this x, it's funny because we were doing these pictures during Easter, so we were studying x, let's say, but these are level set of Lyapunov function. So it appears that for this dynamical system, there is Lyapunov function, which I will show you in a moment. Here's a bit different rescaled variables, and here's Lyapunov function, which, but it's with different rescaling with 4 pi, but it doesn't change much. And this Lyapunov function is global, and you should see that it's singular. And this, the border 1 over 8 pi, when you translate it, it corresponds to the mass connected for the given r with the Schwarzschild radius. So the singularity, let's say, is at the Schwarzschild radius, and it corresponds in these variables to 1 over 8 pi. It's also singular at y equal to 0, but apart from that, in this strip, it's global. So it shows you, this function shows you that this point when the spiral converges is globally attractive. So it has to attract everything. And coming back for a moment to this picture, this is mathematical proof, let's say, that our trajectory cannot cross this blue line. It should turn down on this line. So there are only 2 options. Either it enters here or it enters there. But once it enters there, this gives you the proof for the critical mass. And it's not numeric, it's just the proof. But unfortunately, this proof, as quite often in mathematics, it's not optimal. And this is one was this singularity, as I told you, and there are some estimates just to show you. Mathematical one was, let's say, this one, and numeric one is this one, and you can see how far we are from something that we predict by numerics. But the story here so far was for something not related with this Milky Way and Sagittarius A star, and for this we need another equation of state. So we move to equation of state, and for the equation of state we use such ugly-looking Michie King distribution, which is truncated. This truncation means that the particles with large velocities, they evaporate from the system. So it takes...
So now, sorry, you have the baryonic current.
Yes.
And baryonic mass density in contrast to the common definition.
Yes.
So this is...
Yes. So we are getting step by step. Here's the density, relativistic. Here's the pressure. Here is this distribution in the phase space. P now means not the pressure, but it's just momentum. And P, large P is the pressure. And you have to average over velocity, so momentum, and find the dependence of P on rho. And what is it? What it appears to be? Here is the kinetic average. So it's, sometimes it doesn't work. Oh, yes. So it's quite complicated and it's ugly. So I will just show you two things. That here, at 0, equation of states should be approximately something like that. And at infinity, it should be linear. So this is the formula that was suggested by Ruffini in their paper, and they adapted it to this Sagittarius S2 circling around Sagittarius A star. And they claimed that the data fit the same good as the ones that were suggested by black hole model. And moreover, even not only S2, but also another object which is G2, which there are some, it's not even known whether it has stellar or gaseous structure or whatever it is, but they try to accommodate it both to this S2 and G2 objects and to fit the data. So you see that the formulas are very horrible, but the thing is, this Y that enters here, it's the cutoff value. It's the cutoff value of the kinetic energy. So you see that rho depends only on this Y variable and constant. P depends also on this Y variable. And if you calculate Y as the dependence on rho, the inverse, let's say, of this function, and you plug it here, you end up with the formula equation of state that is P dependent on rho. And the crucial thing is you have 7/5, and here is linear. Apparently these formulas here are quite complicated. So what can you see? You can create some toy model which joins these two asymptotic behaviors, but it's much easier to handle. So that's the idea. But before that, I will show you also some other calculation, a bit simpler. This is without truncation. So still, we assume that there are fermionic particles, but there is no this Michie King truncation with large velocities, and then it's a bit easier, and it gives also the motivation to consider linear models, because here you see that the pressure is intermediate between two linear states. See? Here is 1/3 at infinity, and at 0 there is another. And you should remember that the density is the density of the energy. Of course, call it mass energy, but it's rho is not it's not number of particles, but it's the density of the energy. But and it's much easier in this approach. But the one that was suggested for Sagittarius A star was the previous one. And I have just 1 minute or so. So here are some physical description how this equation of state is created. So what we assume. Here we show some thermodynamic equilibrium and energy conservation. Where does it come from? So for example, the temperature should be radius dependent from the first conservation. And here's some numerics for toy model, but as you can see, we are quite far from that obtained by Ruffini, in which they, for Sagittarius A star, they obtain something like this. Okay? And before showing you some my references, it's nice fragment from reflections of Polish master. It was the interview of Mitchell Feigenbaum, he's from Chaos, with Stanisław Ulam and Mark Katz in Los Alamos. And then they say that there are two acts, understanding and proving, that sometimes you don't understand, but you can prove it, and you can publish it in mathematical journal. And the other way around, that you fully understand it, but you cannot prove it, but still you can put it in physical journal. And the height of happiness is when you both understand and are able to prove it. But this, according to him, doesn't happen that often. And here are some my publications. What I was talking about is not yet published. These parts connected with Lyapunov function and with this equation of state. Some previous. Thank you.
Thank you very much. And now we have time for questions. I have one. In general, you do not necessarily have to have the relation between pressure and energy density. There is the series of exotic singularities nowadays considered for the universe, where they are not related by an analytical formula. And another, it's more like comment. And another thing is that you assumed P equal to rho, equation of state. So you removed 1 degree of freedom, in fact, in your system, because you made pressure equal to energy density, which is still fluid, in fact, in cosmology.
Yes.
So I think if you released, then you would have three-dimensional dynamical system.
Yes, it's true that if you consider that, so the aim somehow is to do something for general pressure rho relation, and then, as you have said, that then you have non-autonomical system, which means that there is also third equation. If you want to make phase diagram or dynamical system. So I fully agree.
That would surely enrich the investigation.
Okay, thank you.
More questions?
Where from you take those fermions?
Sorry?
Where from you take those fermions? Usually people think that black holes are the simplest things that you can have. And you want to have fermions. How do you have them in the center of the galaxy?
In a way, you should address this question to Remo Ruffini, who was in 1971 with Wheeler promoting black hole name in the books and the articles, but afterwards, so what they try to do, one question is how you put them in the core, another is how you put them in the halo. So somehow this density, the aim is to solve two problems, the core and halo, and to give one distribution which would cover both. With these fermions, nobody knows because they put them, they don't know the energy of them. They make it from 50 to 300 kiloelectron volts of these particles. So, and they change these parameters so that to fit the data of this S2 trajectory. So somehow it's so previously there was the Burkert profile. They had the profile like that. It was given ad hoc and it suited to data. Now they show also that if you go from Einstein equation with, let's say, exotic equation of state, but this exotic equation of state has very good history of Chandras Tolman, Chandras Eckhart, Klein, and Michie, who died prematurely, King. So these were the approaches what equation of state would suit it best. But about the nature of these fermions, they called it Dafermos. So even they invent the name for it, so to somehow cope with them. But nobody knows what is inside, and somehow what Genzel and Ghez said, that something massive inside, without giving it name or depicting it, we know the influence through the gravitation. We don't know what is inside, so that's sort of my answer, but I didn't answer. And I don't have ambition to answer such questions.
Chemos are not supersymmetric at all. Sounds supersymmetric. Any other questions?
So implicitly, what would use any other parameterization of the pressure to fit the data better? So you said this is an arbitrary way to fit the data using this parameterization.
Yes,
but in principle search for better ways to fit the data with different kinds of.
Yes, but in this data, what are the parameters is, for example, the energy of the particles. So there are only, you fix only what I mean by data, you fit the constants. But the model and the behavior at zero and at infinity and the nonlinearity is just given. So what you can do is just you change the parameters of the model, but the equation stays the same.
More questions? If not, let's thank the speaker.